everyone, Tina here, and today I'd like to talk about differentiation modelling questions that you'll usually come across during year 1 of your A-level course. I have made other videos on differentiation, so I'd recommend you watch those ones as well. Let's go straight into some examples. Example 1. A cylinder has a radius of r and a height h. The surface area of the cylinder is 500 centimeters squared. Part A. Show that the volume of the cylinder is given by that expression. So for part A, you might want to draw yourself a little sketch of a cylinder. Radius r, height h. We're told that the surface area is 500 centimeters squared. We want to know about the volume. So if we think about the generic volume of a cylinder, that's pi r squared times the height. Now that doesn't match their expression for the volume. If you compare what they want with what we have, hopefully you can see we have a h and they don't. That means there must be a way of rearranging something to get h as the subject. The trick to this is we want to find an expression for the surface area and make it equal to 500 because that's the information we've been told. So generally for a cylinder, the surface area is going to be 2 pi r squared plus 2 pi r h. We're told that that's equal to 500 in this case. So that is where our h is going to come from. All we need to do now is rearrange that expression to make h the subject. So if we do that, h is still here. To get it on its own, we just need to divide through by 2 pi r. Now we're ready to sub this h expression into v. For these types of questions, you just need to get comfortable with the algebra being a bit complicated. So it's pi r squared times that whole expression. We can then look at cancelling. So you could cancel a pi from up there and down there. At that point, I'd probably expand in the r squared, 500 r squared minus 2 pi r to the power of 4, all over 2r, which then simplifies to 250 r minus pi r cubed as required. So just to recap, for questions like this, you want to use the information that's been given, along with general formulas that you already know. B. Given that r varies, calculate the maximum value of v to the nearest centimetre cubed. Now that word maximum should hopefully make you think of stationary points, so where the gradient is going to be equal to 0. Now even if you haven't managed to do part A, you can attempt part B because you just need to use the v equation that was given. That's the equation for v, so if we differentiate this to get the gradient, that's going to be 250 minus 3 pi r squared. Maximum is a stationary point, so we want to set that equal to 0. We're then going to rearrange that for r. When we do that, we get this. R equals the square root of 250 over 3 pi. Just the positive square root because the radius has to be positive. That's roughly equal to 5.15 centimeters. It's worth sense checking that it's not a weird number. But in terms of finding the maximum v, we're going to sub in the exact value. So sub into v. V is equal to 250 r, which in this case was this, minus pi times r cubed. Typing that carefully into your calculator will give you 858.387. So roughly 858 centimeters cubed to the nearest centimeter cubed. Part C, justify that the value of v you found is a maximum. So justifying it's a maximum sounds like we need to prove that the second derivative is less than 0, because on a curve that would look like this. So let's find the second derivative, d squared v over dr squared. In this case will be minus 6 pi r. We're going to use the r value that we found earlier, so 250 over 3 pi all rooted. I'm going to sub that into the second derivative expression. Typing that in, you get negative 97.1, which is in fact less than 0. Therefore, you've justified that it's a maximum. And that's it. Example 2. A company manufactures food tins in the shape of cylinders which must have a constant volume of 150 pi centimeters cubed. To lessen material costs, the company would like to minimize the surface area of the tins. By first expressing the height h of the tin in terms of its radius r, show that the surface area of the cylinder is given by that. Okay, so for part A, we've got a cylinder again. Let's sketch one. Radius r, height h again. This time, the information we're given is that the volume is 150 pi, and that's just in the question there. We want an equation for surface area, so generally, surface area is 2 pi r squared plus 2 pi r, h. Again, the first thing I would do is compare what they want with what you have and figure out what's different. And again, what's different is that we've got h and we don't want it. must mean we have to find h by some other means and then sub it in. So what do we know? We know about the volume. Volume of a cylinder generally is pi r squared h. We know it's equal to 150 pi, so let's write that down. Once again, that's from the question. And then we can rearrange this equation for h. When you do this, you can cancel the pi's, and you're left with h equals 150 over r squared. You're then going to substitute this into your s equation. And when you do this, you get s equals 2 pi r squared plus 2 pi r times 150 over r squared. See if you can cancel anything easily, maybe the r's there, and then simplify. And you will get the expression that they wanted. Part B. Use calculus to find the minimum value for the surface area of the tins. Give your answer correct to 2 decimal places. So this time we've got the word minimum, and hopefully that makes you think of stationary points again. And a stationary point is where the gradient is 0. So we do need to differentiate now. S is equal to 2 pi r squared plus 300 pi r to the minus 1. That is just me rewriting the expression given in part A. So once again, if you can't get part A in the exam, doesn't mean you shouldn't try part B. Let's differentiate that. ds dr, we get 4 pi r minus 300 pi r to the minus 2. We're going to set that equal to 0, and we're going to solve for r. Now this one is slightly more complicated, so what I would suggest is you rearrange it like this. And as you're rearranging it, maybe write it back in terms of fractions rather than negative powers. Reason for this is now we can times up by r squared to get 4 pi r cubed equals 300 pi. And from there, it's much easier because you can just divide through by 4 pi. So r cubed is going to be equal to 75. Pi's cancel and 300 divided by 4 is 75. Therefore, r is just the cube root of 75. We can now sub this into our s equation. So s is going to be 2 pi times cube root 75 squared plus 300 pi over cube root of 75. And that turns out to be 335.23 centimeters squared to 2 decimal places. Now, this question doesn't necessarily say that we need to justify that it's a minimum, but I'm going to show you how to do that anyway. So to do that, we need the second derivative. By differentiating again, we get 4 pi plus 600 pi r to the minus 3. You can then sub in your r value, and in the calculator, that works out to be 37.699 something, which is greater than 0. Therefore, we've shown it's a minimum. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks, and see you next time.